The topic of today's video will be Milne Thomson's method to construct an analytic function. Whenever there is a relationship between u and v, or precisely u or v are given, right? We are given the real or imaginary part of an analytic function, and we have to construct the function, analytic function fz, right? We generally have two or three cases. It is divided into two or three cases. One case is when u is given, real part is given. And then case two, when imaginary part is given. And the third part is that when the relationship between u and v is given, right? Okay. Case A, and this method is used for the construction of an analytic function without finding the harmonic conjugate. Suppose you are given u and you have to find fz without finding v, right? In general, first we find v, then we do fz equal to u plus eta v, as we discussed in our last video. But using this method, we can directly find an analytic function fz without finding v or u. Means one of them is given, u is given, then you will directly be able to obtain fz, right? Case A, if the real part, right, u is given and f equal to u plus eta v is analytic, right? You are given the real part of a function and you are searching for the analytic function f, right? Then this method says that first you find del u by del x, obtain del u over del x and del u over del y, right? Let phi 1 x comma y equal to del u over del x and phi 2 x comma y equal to del u over del y, right? Obviously, these partial derivatives are functions of x and y, so we have written phi 1 function of xy and phi 2 is function of xy, right? Okay. Now, using the formula for f dash z, and that is actually del u over del x plus eta del v over del x, right? This is the formula you use to find the derivative of an analytic function, right? Or you can write it as, or f dash z can be written as x plus eta y, fine, equal to del u by del x is del u by del x minus eta times del u by del y. I have used CR equation here, one of the CR equation. I will write it here, use CR equations, right? And now you can see that I can write it as phi f dash x plus eta y equal to del u by del x is actually equal to phi 1, a function of x and y, minus eta times phi 2, function of x, y, right? So you can see that the derivative is just the phi 1 minus eta phi 2, and you can integrate it in order to obtain fz. But one thing is that you want fz, right? You want fz, analytic function fz in terms of z. So you can replace these x and y by, if you see that, you know that since z equal to x plus eta y, you know that, right? And its conjugate will be given by x minus eta y, right? Okay. And if you add them, then you will get the value of x, and if you subtract these two, you will get the value of y, right? Implies x equal to, on adding them, I will get z plus z bar over 2, z plus z bar over 2, and y equal to z minus z bar over 2 eta, right? And I will plug these values of x and y here in my relation, right? Equation number 1. Then first becomes, in terms of z and z bar, f dash, and the value of x is z plus z bar over 2, z minus z bar over twice of eta, equal to phi 1 z plus z bar over 2, z minus z bar over 2 eta, minus eta phi 2 z plus z bar over 2 and z minus z bar over twice of eta, right? Now we have f dash in terms of z and z bar, right? But what is my target? My target is to search an analytic function fz, f in terms of z only, right? You don't need z bar here actually. So this is an equation, or this is a relationship, right? And this relationship holds for all values of z, right? And if I put z equal to z bar here, then this relation will also be true again, right? Put z equal to z bar. This will be treated as an identity, like you have sin square theta plus cos square theta equal to 1. It is involving theta, and it is true for all values of theta. Similarly, we have an identity in terms of z and z bar that should be true for all values of z and z bar. So I have chosen z equal to z bar, and the choice of the selection is important. Why I have selected z equal to z bar? Because that will produce 0 here, right? And obviously, and everything will be converted in terms of z, because I need fz, right? And then I will get f dash, and this will be z plus z by 2, right? And that will be ultimately z, right? And this will become 0, right? Equal to phi 1 z comma 0 minus eta phi 2 z comma 0, right? I think we should write it as only z. There is no need to write it as, I should write it as f dash z only. F dash, where is that? F dash z, and since you are choosing z equal to z bar, right, means a complex number is equal to its conjugate, and that is possible if and only if that complex number is a real number, right? I mean, you can write it as x plus eta y equal to x minus eta y, right? Or it means that then x and x will be cancelled, and you will get y equal to 0, right? And if y is equal to 0, you can see that this is x plus eta y, right? Then you will get a x equal to z, right? Because y is equal to 0, this implies z equal to x only, right? That's why I have replaced this x plus eta y by z, right? Or should I write it as x plus eta y, x is replaced by z, right? Now this is fine. Okay, so this is the relationship for f dash z, and you want to obtain fz, you will integrate it on integration fz equal to integration phi 1 z comma 0 minus eta phi 2 z comma 0, and integration will be done with respect to dz, and then plus c will be a constant, right? Plus c is the constant of integration, and you have to remember this formula for the numericals for the case when u is given, right? Okay. Now I will take case number 2. If v is given, right? Case 2. Case 2. If v is given and f equal to u plus eta v is analytic, right? You are given the imaginary part of an analytic function, and you are searching for the analytic function f, right? So proceeding similarly, we will first obtain del v over del x and del v over del y, right? Then let phi 1 x comma y equal to del v over del x and phi 2 x comma y equal to del v over del y, as we did in that case, right? Then using the formula for derivative, that is f dash z equal to del u over del x plus eta del v over del x, right? Okay. Now comes the use of CR equations, because I have del v by del x and del v by del y, means partial derivative of v, and we have this u here, so this will be replaced by using CR equations, right? So this will become f dash x plus eta y, because that can be written as x plus eta y, equal to del v over del y plus eta del v over del x, and using CR equations, right? Okay. Now we can plug the values of the derivatives of v, x plus eta y equal, this is actually del v by del y is actually phi 2 this time, phi 2 x comma y, and del v by del x is actually phi 1 this time, plus eta phi 1 x comma y, right? And this is my equation number 1, and giving the same argument as I have given here, because z is actually x plus eta y and z bar equal to x minus eta y, adding and subtracting them will give x and y in terms of z and z bar, and plugging those values here in equation number 1, right? Similar or using this argument, I will get f dash z equal to phi 2 z plus z bar over 2 z minus z bar over 2 eta plus eta phi 1 z plus z bar over 2 z minus z bar over 2 eta, right? Fine. And then again putting z equal to z bar, put z equal to z bar, right? And if you put z equal to z bar, you are assuming that a complex number is equal to its conjugate, and that is only possible if and only if z is equal to a real number, that is z is equal to x, right? Or z equal to x, right? For the proof you can see this will give z equal to x, right? Then this will give f dash z equal to phi 2 z comma 0 plus eta phi 1 z comma 0, right? And on integration, fz equal to integration of phi 2 z comma 0 plus eta phi 1 z comma 0 dz plus constant of integration c, right? So you can see the small difference in these formula. Here we have phi 1 minus eta phi 2, whereas in this case we have phi 2 plus eta phi 1, right? So two cases for u and v, and now the third case when the relationship between u and v is given, right? And generally it is of the form u plus v or u minus v, right? So that is by case number 3. Case 3, if u plus or minus v is given and fz equal to u plus eta v is analytic, right? So this time not precisely u and not precisely v is given, rather you are given a relationship between them, that is u plus v or u minus v, right? I am writing that as a single case, u plus v or u minus v, anything can be given to you, right? In that case you will obtain del u over del x plus minus del v over del x, right? Or you will obtain yeah, that's fine, right? You will obtain the derivative of this relationship with respect to x, right? And use CR equations. And one more thing, del u over del y plus minus del v over del y. You will differentiate this relation with respect to x once, and then with respect to y the second time. Then you will have two relations. One is this one and the other is this. Then you will add and subtract them using CR equations to obtain u, right? Use CR equations, right, to obtain del u over del x and del u over del y, or you can solve them to obtain del v over del x and del v over del y. You can choose either of these cases, whether you want the whole problem in terms of u, right, and then proceed accordingly as we did in case number A, right, or you can convert these equations in terms of v, right, and then solve them to obtain del v by del x and del v by del y, and you will go to case number B, right? So case number 3 is just a combination of case number 1 and B. You can case number 1 and 2, right? You can convert this case, right, as in terms of case A or case B, right, and then proceed as in case A or B, right, respectively. Okay, so these are the three cases, and we'll take an example of these cases one by one. First, I will take a real function u is given, and we'll look for an analytic function f equal to u plus eta v, right? And let me take example number one. Suppose u x comma y equal to x square minus y, or should I take it at cubic function x cube, and then it will be minus 3 times x y square, fine, x cube minus 3, yeah. Such that fz equal to uxy plus eta v as a function of xy is analytic. Find fz, right? So you are given the real part of an analytic function, imaginary part is not known, and we are interested in finding the analytic function fz without even finding this harmonic conjugate v, as we discussed in our last video, right? Solution. First, I will obtain the partial derivatives of this u with respect to x and with respect to y. That is del u over del x equal to how much? 3x square and minus 3y square, and we will call it function phi 1 x comma y, right? And then I will obtain del u over del y, and that will be minus 6xy, and we'll call it function phi 2 xy, right? And then we'll directly apply that formula as we obtained for case number A, right? But to apply that formula, we need phi 1 z comma 0 and phi 2 z comma 0. You can see from here, right? This for V. We have that for U also. Okay, so I will obtain phi 1 z0 and phi 2 z0, right? Okay. Should I write that formula directly? What was that formula? Then, using Milne Thomson's method, the formula for this case was actually integration del u over del x, that is phi 1 z comma 0, and that was minus, okay, eta times phi 2 z comma 0, and here we had dz and constant of integration c, right? Now you can put phi 1 z comma 0, substitute x equal to z and y equal to 0, you will get 3z square, 3z square minus eta times phi 2 z0, and if you put x equal to z and y equal to 0, you can see that this term will vanish, 0, right? So it is 0, eta times 0 dz plus c, and you can integrate it. Integration will give you z cube plus c. So this is your fz, right? And you can see that, however, it is not asked in question. If I add one more thing, also obtain its harmonic conjugate, its harmonic conjugate Vx comma y. If this is also asked in question, then what you will do, you will substitute z equal to x plus eta y, and then open it up. Also fz equal to x plus eta y whole cube plus c, and then you can open it, and on opening it you will get x cube minus eta y cube plus 3 eta x square y minus 3 xy square plus c, right? And you need actually, fz is actually u plus eta v, you know that, right? And on comparing, you get v is equal to, the imaginary part should be equated, that is v will be equal to, the imaginary part of this will be with that 3 x square y minus y cube, right? Fine. So this is your v, right? And you can also you can add c here, because c is either present in real part or imaginary part, because this can be c or eta c, right? We don't know. So since the real part is not containing c, right? it means that the imaginary part will contain C, right? So this is a V. Okay, so this is an example for case number 1. Now I will take the example for case number B when V is given, and you should remember this formula. In that case, phi 2 comes first and then plus I2 times phi 1, right? Example number 2, construct an analytic function fz equal to u plus iota v if v is given this time and v is equal to let me take it e to the power iota z e to the power minus y and sin x, right? Okay, so this is given, v is given, right? Fine. Solution. Okay, since v is given, we will obtain obviously the partial derivative of v with respect to x and y. There is no choice. Del u, del v over del x is equal to e to the power minus y cos x, and let me call it phi 1 z comma 0, and del v over del y is equal to negative of e to the power minus y sin x, and let me call it phi 2, sorry, x comma y phi 2 x comma y, right? And now we'll use the formula directly, right? Using the formula for this case, when v is given, and that formula is actually equal to fz equal to integration, first comes phi 2 z comma 0, and then comes plus iota phi 1 z comma 0, and here we had dz plus c, right? Fine. And then plugging these values here, integration fz or phi 2 z comma 0, this is my phi 2, put x equal to z and y equal to 0, you will get minus sin z, right? Minus of sin z, minus sin z, and plus iota phi 1 z 0, put cos z dz plus c, right? And you can integrate it with respect to z. You will get integration of minus sin z will be cos z plus iota sin z plus c, right? And yes, or you can write it as or fz equal to e to the power iota z plus c. This is also possible, right? Cos theta plus iota sin theta is e to the power iota theta, right? So this is the analytic function for which the imaginary part was given, right? Okay, now I will take the example for third case when a relationship between u and v is given, and we know that we convert the problem either similar to case number A or case number B, right? I will convert the problem for according to the case number A when u is given. Everything will be converted in terms of u, right? So example number 3. If u, let me take it to u plus v or u minus v. Okay, we will take u plus v, right? U plus v equal to e to the power x cos y plus sin y, right? Such that fz equal to u plus iota v is analytic, right? Find fz. Okay. So a relationship between u and v is given, and their sum is given. So the only choice you have is to differentiate this with respect to x once and then with respect to y, right? So differentiating this with respect to x, and that will produce del u over del x plus del v over del x, and I will write it ux or vx, right? Differentiating partially with respect to x and then y one by one. First I will differentiate it with respect to x, and that will produce ux, it means that del u by del x plus Vx equal to, with respect to x it will give e to the power x cos y plus sin y, right? And okay, and I have something in my mind. I want to convert this problem according to case number A, right? When u is given, so I want u everywhere. At this place I have u, but this is not u. I will convert it in u by using CR equations, right? And I know that minus of uy is equal to Vx, right? So should I write it as, or ux minus uy, right? Vx is equal to negative of uy by CR equation is equal to e to the power x cos y plus sin y. I will mention here using CR equations. One of the CR equation, only one equation I have used. Okay, this is my equation number 1. I will call it equation number 1. Equation number 1. Fine. And now differentiating with respect to y, the given relation, and uy plus vy equal to, its differentiation with respect to y will give minus sin y plus cos y, right? And again I want everything in terms of u, so I will change it. I will write ux in terms of vy, or ux plus uy plus ux, or fine, uy plus ux equal to e to the power x, and should I take it common? No, e to the power x minus sin y plus cos y, and this is my equation number 2. Again I have used CR equation, and this is my equation number 2, right? And then this is my equation number 1, equation number 2, right? And if I add equation number 2, and if I add them, right, these two equations, then this uy will be cancelled out, and I will get ux, right? And then subtracting them, I will get to uy, right? So first plus second, if you add those two equations, you will get uy will be cancelled, twice of ux, right? And I think this minus sin y will be cancelled, twice of ex cos y, right? And ultimately that will produce ux is equal to e to the power x cos y, right? And if I subtract them, second minus first, right, of first minus second, okay, then it will produce second minus first, then that will produce uy obviously equal to, and I think cos y will be cancelled, and e to the power x minus e to the power x sin y, right? Fine. Okay, then these are my ux and uy, and let me call it phi 1 x comma y, because the derivative with respect to x is denoted by phi 1, and the derivative with respect to y is denoted by phi 2, right? And then since I have everything in terms of u, right, derivatives of u are present, so I will use the formula for case number 1, and that formula is using fz equal to integration. Here we had phi 1 z comma 0 minus eta phi 2 z comma 0 dz plus c, right? Okay, fine. Then I will plug the values of phi 1 z comma 0. Phi 1 z comma 0 will be e to the power z, I think, yeah, e to the power z minus eta, and phi 2 z comma 0 will be 0 dz plus c, and on integration it will produce e to the power z plus c. This is my answer, this is my fz, right? Fine. Okay, so similar is the case when u minus v is given, right? You can construct an example similar to this, just write u minus v equal to e to the power x cos x minus sin y, right? And then you will solve it, and then you will again get the same answer, e to the power z plus c, right? That is pretty similar to this one, right? So I will take another example different from these three examples, and that example number 4, And if I take if imaginary part, this is imaginary part of f dash z is equal to e to the power x sine y, right? And f0 equal to 1 and f1 equal to small e, then find an analytic function fz equal to u plus eta v, right? Okay, so here we are given the imaginary part of f dash z, derivative of f, and that is actually equal to e to the power x sine y, right? And f, the value of f at 0 is given, the value of the function at 1 is also given, and you have to search for that analytic function fz equal to u plus eta v, right? So this type of problem can be done by starting with this one. What is given? Imaginary part of this one. Since imaginary part of f dash z, and you have to remember the formula for f dash z, the basic formula we have been using, f dash z is equal to del u over del x plus eta times del v over del x, right? So this is actually equal to f dash z is actually equal to del u over del x, right, plus eta times del v over del x, right? Fine. And then this is actually equal to e to the power x sine y. Okay, then what will we do? Imaginary part of this one, it means that picking up the imaginary part, because here it is an imaginary part of this complex function, we'll get vx equal to e to the power x sine y, right? Because imaginary part is vx, right? And now we have v, right? So you have del v by del x, but you don't have del v by del y. Actually this problem is moving towards the case number b when v is given, but something is missing here. We have del v by del x, we should have del v by del y, right? And I have to obtain del v by del y from here only, because I don't have anything else, right? These are the conditions for f, not for v. So what I will do, I will write it as del v over del x, that is obvious, or del v over del x is equal to e to the power x sine y, and now I can integrate it with respect to x, because this is del x will appear here, and integration both sides with respect to x. On integration with respect to x, obviously, because del x is present here, that will produce v as a function of xy, okay, is equal to integration of this thing with respect to x will give e to the power x sine y. And since we are doing integration, and again there is a partial derivative, not the ordinary derivative, so we cannot write plus c here. Constant of integration is written whenever we are dealing the integration of a single valued function, or function of one variable more precisely. But this is a function of two variables. When we integrate the function of two variables, then we don't write plus c, we write fx or fy, depending upon the variable for which we are integrating for, right? We are integrating for dx, so I should write it here fy, right? Because everything that is a function of y will be treated as constant here, right? So plus fy, and you should note this step why I have written fy, right? Because integrating with respect to x will give a constant, and that constant is actually a function of y, right? Okay, now I have v, okay, fine, I have vx, fine, I have v, yeah, I can obtain del v by del y from here, because I am having del v by del x, right? I should have del v by del y, right? And then I will jump to case number b. So differentiating with respect to y, note that I integrated it with respect to x, but I will differentiate it with respect to another variable y. Differentiating partially with respect to y, and that will produce del v over del y equal to e to the power x cos y, and this will be f dash of y, right? Now I have vx and I have vy, and I'm almost at the door of the case number b, right? and should I write it as phi 1 x comma y, and should I write it as phi 2 x comma y, right? Now I will apply that formula for case number B, and that formula is using the formula for case number B, that is fz equal to, I think here we had del u by del x, del v by del y, that is phi 2 z comma 0, and here we had eta, right, plus eta, okay, and phi 1 z comma 0 and dz plus c, right. Now I will plug the values of phi 2 and phi 1, right, or fz equal to integration the value of phi 2 z comma 0, phi 2 z comma 0, replace x by z and y by 0, you will get e to the power z, and cos 0 is 1, plus f dash 0, right, plus eta times phi 1, this is phi 1, this is my phi 1, z comma 0, and that will be 0 dz. Okay, plus c, right, and on integrating it I will get e to the power z plus z times f dash 0 plus c, right. Okay, so this is the value of the function, right, but it is containing an arbitrary constant c, an arbitrary function f, means two arbitrary things are present in my function, and obviously I have two conditions to find them, right. I will use these conditions one by one. This is fz, okay, I will call it equation number 1 using, since f0 equal to 1, I mean put z equal to 0 and fz equal to 1, I will have 1 equal to 1 plus c, and that will produce c equal to 0, and having c equal to 0, my equation 1 reduces to 1, reduces to fz equal to e to the power z plus z times f dash 0, fine. And now I will use my second condition, since f1 equal to e, that will produce e equal to e plus f dash 0, and that will produce e will be cancelled, f dash 0 will be 0, implies f dash 0 will be 0, right, and I will plug this f dash 0 in my last solution, and that was my equation number 2, right. Second reduces to fz equal to e to the power z, right, and this is the final answer, right, is the required analytic function, right. So that's it, and we can construct another example. Rather than writing imaginary part, we can write a real part of f dash z, right, and then I think here we will have real part of this, and here I will have ux, right, and then the problem should be targeted to the case number A when we have u, right, similar to this one, right. You can construct that example of your own and try to solve it out, and this is it. And you can see that this Milne Thomson's method has only one advantage as compared to a last video where we looked for the harmonic conjugate, that is u is given and you look for v, right, and then you construct fz, right, means to construct an fz you needed v, right, and but in this method you don't need actually the harmonic conjugate. You are given u or you are given v, you can directly construct the fz by using this method. This is the only advantage that this method has over that previous method, right. So that's it for this video. Thanks.